All right, so over the next few days, we are going to talk about a variety of different forces. Now, you've met most of the forces that we're going to be talking about, but we're actually going to do some examples involving these types of forces, specifically focusing on applications of Newton's second law. And if you're keeping track at home, that would be chapter 5. All right, so we're on our way forward. So let's list a few types of forces that you may be inclined to come across. Now, you've already met the force due to gravity. I'm not going to be redundant, so I'm just going to write gravity. The gravitational force, that's certainly a force. Give me some other forces that you'll encounter here that we'll deal with. Tension. All right, certainly tension. What else? Friction. Air resistance is a force. What else? Yep, normal force. You're going to see that. All right, so those are the primary forces we're going to be dealing with. There's a few others that bear mentioning. One of the forces that we're going to deal with is due to like a spring. We could call it an elastic force, or just call it, forces due to springs. So spring force or an elastic force. Right. Another type of force that we won't deal with, that we won't see in this class, you'll see next semester. Specifically, it's a type of force that we consider to be a non-contact force. So most of these forces are contact forces. So these guys are all contact forces. And what I mean by that is that, there are two objects that are touching each other, and one's exerting a force on the other and vice versa. All right, so in tension, in the case of tension, there's a rope or a string or something that is touching an object and exerting a tension force. Friction, there's two surfaces that are trying to move relative to one another. There's a contact there. Air resistance, air is stuff, all right? There's mass in the air contacting the object that you care about. So these are all contact forces. Gravity, however, is a non-contact force. You don't actually have to be touching the thing that is exerting a gravitational force on you. Just like if you jump off the ground, Earth is still pulling you back down. All right, so there's a couple other non-contact forces that you're probably familiar with. We just won't talk about in this class, other than right now. So what are those? Not resistance. All right, electric. So a little bit more fundamental than resistance. So electric and magnetic forces. And you can look forward to learning about those in Physics 224. They make the world go round. All right, so those are the forces that we're really going to deal with. You've already met most of these, so we're just going to work on applying. Some of these. All right, so the first one, let's start off and do a relatively simple example in that we only have a couple forces, and this is the person in an elevator problem that you just kind of looked at a little bit, maybe in the quiz. So the question is this. How much do I weigh? And I want to put weigh in quotes, not semicolons. How much do I weigh in an elevator that is moving upwards and accelerating at 1.2 meters per second squared? So I really like this problem because it's to really understand what's going on here, you have to understand all of Newton's laws. Okay, so let's draw a picture and try to see what I mean. I want to know, you're in an elevator, right? And the elevator starts to accelerate upwards and you jump. And it feels weird because you hit the ground a lot sooner than you expect. Right? You've all experienced this. You'll experience it if it's been a while. When you have kids, you'll experience it again. Right? You got to teach your kids when to jump. So really, what's happening here is, when the elevator starts to accelerate, do you feel like you're the same weight? Do you feel heavier? Do you feel lighter? You feel heavier, right? If the elevator is accelerating upwards, you feel a bit heavier for that instant. And so the question is really why. So what are we looking at here? Well, we're looking at a scale. if we had a scale and an elevator and you stood on the scale. All right, we want to know what that scale would read. All right, now we expect that it reads a number larger than what I weigh in real life. All right, so let's give some numbers here. So I think the only number that we really need is a mass. We'll consider the mass of me or the mass of the person to be 70 kilograms. Now the problem is we need to sort of identify the object that we care about in this example. What is the object that we want to draw a free body diagram for? Wait, I think I heard all of them. I heard person, I heard scale, and elevator. That's awesome. That's good. That means there's some learning to be done. All right, this is actually really tricky because I'm asking how much do I weigh? You know, so you're like, okay, we care about the person, right? But, you know, I weigh, what does that mean? I mean, that really means what does the scale read, right? So really what we want to do is we want to apply Newton's second law to the scale to figure out what the scale reads. All right, and let's do that, and we'll see why in a bit. So the scale is a box. The scale has a few forces acting on it. All right, what are the forces acting on the scale? Person. The force of the person. So we'll call this F sub P, which is also equal to the weight of the person. Okay? What other forces?
Gravity, normal force.
All right, so there's a normal force, and then there's gravity. Good. So now the question is, though, you know, which force is the scale actually is the scale reading out? What is the scale reading, giving you?
It's your weight plus the force of
Is the scale reading its own weight?
No, if the elevator is just not moving, it's just the weight of the person since normal and gravity takes out each other, so it's only the person left.
Well, usually the scale is just calibrated so that they don't read their own weight. It couldn't be perfect.
All right, so it's sort of a tricky thing, and this is sort of a tricky picture because if you start to really get down into like the details, well, the scale isn't just a box; it's got springs and all this other stuff. But the scale is actually reading this value right here, the force of the person, the weight of the person, or else it wouldn't really do much good, right? This force is related to another force not in this picture. What force is that? Gravity. I don't know. It's on a different object. It's on the force that's acting on the person. So if we draw a free body diagram on the person, what do I have? The force of the scale on the person, which we could consider to be a normal force, right? It's just the scale supporting. And then the person also has what? What else? Gravity. Is that it?
Does the person have a normal force on the scale?
So that's what the force of the scale is. So you could say this is the normal force. Oh, are you asking, does the person exert a normal force on the scale? Sorry. Yeah, and so we wrote that as the force of the person. So this is also, you could write this as the normal force. All right, so this is the normal force due to the scale on the person. This is the normal force due to the person on the scale. This is the thing that the scale actually reads. All right, that is an action-reaction pair, a third law pair with this force. I like to call them third law pairs. All right, so what Newton's law says is in order to really figure out what the scale reads, this problem becomes a little bit more complicated, right? I've actually got to think about the scale because this is the thing that the scale reads, this normal force, this force due to the person, all right? But in order to figure out the value for this force, this free body diagram doesn't really help me at all. Right? Because, well, I can sum all these things up, but the normal force, due to the ground on the scale and gravity, those don't help me. I don't know what the mass of the scale is. Those aren't going to tell me anything. Okay, so in order to figure out what this value is, the value that the scale actually reads, I need to use Newton's third law to connect this value with the person. And this is where things get, complicated, is identifying, is realizing that these are third law pairs. I care about this value, which means I also care about this value, the normal force acting on the person. And now, using this free body diagram, I can actually solve the problem. Because I know the weight of the person. I know the force due to gravity acting on the person. Now, I put weight, I put weight here, misspelled, in the problem in quotes, because I don't really want the weight of the person. We know what weight is, right? F sub g, that's the weight. That's defined as the weight. It's equal to mass times gravity. Right? Well, I know that the person weighs 70 kilograms. I know that g is 9.8 meters per second squared. So then I know that the force due to gravity is something like 700 newtons. His weight, his actual weight, is 700 newtons, but that's not what the scale reads. So that's why I put weight in quotes. So how do I figure out what the scale reads? What do I have to do? What am I solving for?
Figure out the new acceleration, and then you can solve for ma equals the new weight.
Okay, I know the acceleration is upwards at, what did I say, 1.2? 1.2. 1.2 meters per second squared. So I need to apply what? Newton's second law in the y direction. All right, and that's going to be equal, and I'm going to set the result of summing up all my forces, and that's got to be equal to the mass times acceleration of the thing that I drew the free body diagram on. All right, so I only have two forces. I have the force due to the scale, or what we call the normal force. I'll just write the force due to the scale. And the positive y direction and the negative y direction I have the force due to gravity, which I already solved for, is equal to 700 newtons. That together has got to give me a mass times an acceleration, and I know I'm accelerating at 1.2 meters per second squared. So that term doesn't go to 0. I'm solving for the force due to the scale, so it's got to be equal to ma plus mg. Now already, I can look at this solution, even though I didn't put numbers in, and I can say, okay, I think this makes sense, because I can tell that the force of the scale, the thing that the scale reads, the number the scale reads, has got to be greater than my actual weight, because I'm adding something else to it, something else that's positive. That's what I expect. So I know that I've done the problem correctly, or I at least have a good inclination that I've done the problem correctly up until this point. It makes sense. This is one of the reasons why I solve in terms of letters, because it's usually easier to look at the physics and say, okay, that makes sense. Right? And once I'm sure that that makes sense, I can go ahead and plug things in. So the mass is 70 kilograms. The acceleration is 1.2 meters per second squared. I add to that the force due to gravity, which is 700 newtons. I already solved for that. And if you do the math, you get something like 770 newtons, about. All right, so you feel like you weigh an extra 70 newtons. And that seems reasonable. When you're going up or when you're accelerating in an elevator, you feel a little bit heavier. You don't feel twice as heavy. You feel a little bit heavier. Right? But it's not that your weight's changing. Your weight hasn't increased at all. All right? It's just that you're accelerating. All right? So since you're accelerating, that makes things feel a bit different. All right? Questions about this problem? Simple free body diagram, but complicated stuff going on here with these third law pairs and identifying what we actually want to solve for versus how we need to go about solving it. All right? So I want to make sure that you understand the link here and to be able to get this. Now, I remember when I first learned physics back in high school, and everybody does this sort of problem, or most people do this sort of problem, and I never really understood this link. You can sit here and you can mess around with Newton's second law until you come up with this, because you sort of have an inclination that, well, I feel heavier, so the equation should look like that. So that's fine. If you could do that, that's great. But making this final step and realizing that the thing that we're actually looking for is part of the scale. It's not the person, it's part of the scale, and that Newton's third law links the two. That tells me that you sort of have an understanding at this level, at Physics 223 level. So that's what I'm looking for, right? Just so that you know. All right, any questions? Good? No? Moving on. Okay, so let's talk about some other contact forces and start to have fun with inclined planes. So the next example involves a sled. A sled on a plane. And the sled is tied to a tree, and it's on a frictionless plane, because it's on frictionless snow, frictionless snowy hill. If the sled weighs 77 newtons, I want you to find the magnitude of the tension and normal forces that are acting on the sled. All right, so we just have a sled on some nice frictionless snow, which we'll have soon enough here in Michigan, and it's tied to a tree. The picture looks like this. Up here, there's a tree, and tied to it is our sled. All right, that's a horrible sled. So it is. Okay, so we're looking at the sled, and we want to find the magnitude of the tension and the normal forces. Well, that sort of reminds you that there are tension and normal forces acting on the sled, but that shouldn't be too surprising. All right, so let's label the forces. Let's draw our free body diagram. Now I'm gonna do that just on my picture here. So tell me what are the forces and what are the direction of the forces?
The normal force is perpendicular to the incline.
All right, so the normal force is always normal or perpendicular to the thing that to the surface that the object is resting on. So the normal force is up and to the left a bit. All right, good. What other forces?
Gravity, straight down.
Gravity always likes to point straight down. All right, don't try to assume gravity goes down the slope. Gravity wants to go straight down, right towards the center of the earth. All right, one more. The most obvious one is tension. Tension goes right up the slope to the tree. All right, let me tell you something about this angle that might help us solve this problem. The angle of the slope is a severe 30 degrees. Right, so this will be a fun ride down for whoever decides to go on the slide when we cut the string. All right, so those are our three forces. So this is a Newton's second law problem. Now we're going to have to apply it in 2 dimensions, though. So we're going to have to do a little bit more work than we've had to do in the past. And just because we're going to be doing a little bit more work, I'm going to go ahead and define a coordinate system. So let's say that we'll just use our standard x and y horizontal and vertical coordinate system. Okay? Now the sled's just sitting there. It's not accelerating, so that'll make our life a little bit easier at least. All right, but since this is a two-dimensional problem, what do we have to do with these forces before we can actually apply Newton's second law? Break them up into their components. So don't forget about components. All right, you have to remember to break things up into their components. So we can do that, no big deal. In the x direction, let's figure out what forces we have. Well, it looks like tension is applying in the x direction. So T sub x, there's got to be an x component of the tension. There's got to be an x component of the normal force, N sub x. All right. I will help you out a little bit here and draw a green dashed triangle for each of these two forces. Okay. I'm going to, so we're solving for T sub x, which is this guy, and N sub x, which is hard to see, which is that guy. All right, so tell me about T sub x. How do I solve for that? What do I need to know? What is T sub x in terms of just the tension T?
It's the magnitude of T times cosine.
Cosine of 30. Good. All right, you can see that because this angle right here has got to be 30 degrees. It's the same as this angle down here. All right, because we're going from the horizontal up to our slope. All right, and of course the horizontal is our x-coordinate. Good. What about n sub x? All right, n sub x has got to be equal to the normal force times some trig function. So what is it? Cosine of 60. Good. This angle can't be 30. If we actually draw in another side here, this angle is 30. 30 degrees. All right, so if this is 30, that means this angle is 60. So it's cosine of 60 or sine of 30, whichever one you like. I'm going to go sine of 30 just to be different. Okay? Now, you can think back to your geometry days or your trig days and remember, how to do that. For me, the way that I always look at these pictures, and this is just to give you another way to approach this, I always like to rotate. In my head, I make these rotations. So whenever I'm trying to figure out an angle, I always try to start from my coordinate axis, which is either the horizontal or the vertical. I know that the slope is 30 degrees up. So I start from my x-axis and I rotate 30 degrees up. All right, so that's what I did here. I started from my x-axis, rotated 30 degrees up, and found tension. That's tension. All right, well, I know that the normal force is 90 degrees away from the tension because they're perpendicular. So if this red line is 90 degrees from this red line, and this green line is 90 degrees from this green line, that means these two angles are the same. The angles between the green and the red lines are the same, 30 degrees. All right, so pictorially, that's how I do it in my head. You can figure out angles however you want. I'm sure you learned how to do this in trig and geometry, but that's my thought process. Okay, so that's fine. We can solve these things, except that we don't know tension and we don't know the normal force. So that's as far as we can get right now. We're just going to have these two equations with a couple unknowns. So we'll have to come back.
I have a question.
Yes, ma'am.
And then wouldn't the x component for the normal force be negative since it's the opposite direction of tension?
Absolutely. So we can put that in now. So I was going to try to catch you on that later, but that's fine. We can do that right now. We know that the normal force is pointing to the left of the vertical. In other words, the x component of the normal force is pointing to the left, which is the negative direction. So we'd better make sure that we include the negative sign. Very good. Okay. Forces are vectors, so signs are important. All right, tension, the x component of the tension is pointing to the right, so that's positive. Cool, so let's do the y direction. So t sub y. If t sub x was t cosine 30, then t sub y is probably going to be t sine 30. And then the same thing for the y component of the normal force. We're going to have n times cosine of 30. All right, should those be positive or negative? All right, good. They're both pointing upwards. The components are over here. Here's t sub y. Here's n sub y. They're both pointing upwards from the center of our object, so we know that those are both positive. Good. So those are the components. We're missing one force. The gravitational force, of course, is just m times g. That lies along our y-axis, and it's pointing downwards, so we do want to stick a negative sign in there. All right, so now we have all the components of all the forces that we need to add together, and we can go ahead and apply Newton's second law. So let's do it. Let's start off and do it in the x direction. It doesn't really matter. You're free to choose. But you have to apply it in both directions. So in the x direction, we know that the sum of the forces in the x direction is equal to the mass times acceleration in the x direction. That's okay because there's no acceleration at all in this problem, so this goes to 0. The right-hand side of Newton's second law goes to 0. So all I'm left to do is sum together the x components of my force. I've already written those down right here, so it's just rewriting them. T cosine 30 minus n times sine of 30 is equal to 0. All right, that's Newton's second law, written out in all its glory. Now the problem is I don't know t and I don't know n. I can't solve that. I've got one equation and two unknowns. I can't solve that equation. I need another equation. All right, so that's fine. I can find another equation if I turn to the y direction. All right, in the y direction, we write down the sum of the forces in the y direction is equal to mass times acceleration in the y direction. We're not accelerating, so that guy is 0. Again, I've already written down all the equations that I need. So I'm just going to rewrite them. T times the sine of 30 plus n times the cosine of 30 minus mass times gravity is equal to 0. All right, so I'm just applying Newton's second law in one direction. Same sort of deal here. I don't know T and I don't know N. I know mass times gravity, but now I still have two unknowns. Now I have two equations, so that's fantastic. I can solve this. All right, how would you guys go about solving this problem? You remember how to solve two equations simultaneously? What? Okay, so solve one for one of the unknowns and plug it in for the other one. That's fine. That's how I would do it. So I don't know that it matters too much. I'm going to go ahead and solve this one for, what did I do? I did t. So this one I say t is equal to, if I solve for t, it's going to be equal to n times sine of 30 divided by cosine of 30. In other words, t is equal to n times tangent of 30 degrees. All right, I can take that and I can plug that guy in right here. So what we're going to get is n times tangent of 30 times sine of 30 plus n times cosine of 30 minus mg is equal to 0. All right, and I can solve that now. I've got one unknown n, tangent of 30, sine of 30, cosine of 30. Those are just numbers. And mg, if you remember back to the original problem, that's just 77 newtons, right? 77 newtons. So I can solve that. If you go ahead and solve that for n, you should get something like 66.7 newtons. 66.7 newtons. Okay? And then you can plug that guy back into the normal force up here and solve for tension. And you'll find that tension is something like 38.5 newtons. Okay, so you can solve that problem. Now there's something interesting here. In order to get the solution, we had to simultaneously solve two equations for two unknowns. Now we could do that, and we did that, and that was fine. And it wasn't so terribly difficult because we only had three forces. But if we had more than three forces, and maybe like we didn't have a string here, we had friction and this thing was accelerating, that problem could start to become a little bit of a bear, and we could become prone to making mistakes. So we can actually do this problem in a different way to make it a bit easier on ourselves. And some of you probably have done this already. And the way that we can do that is we can say, well, wait a second. You know, I've got two forces that are perpendicular to each other. Tension and the normal force. Now, the way that I set up this problem, I didn't exploit that. And what I mean is I ended up having to solve for the components of those two forces. But, you know, if I'd made use of that, if tension was lying in the x direction and the normal force was lying in the y direction, I wouldn't have had to break up those things into their components. I just would have had to break up the force due to gravity. But that's, you know, instead of breaking up two forces, now I'm only breaking up one. That's a little bit easier. And on top of that, since I was solving for tension and the normal force, well, then tension would only apply in the x direction. The normal force would only apply in the y direction. So I wouldn't have to solve two equations simultaneously. The x direction would tell me what tension is. The y direction would tell me what the normal force is. So I wouldn't have to do any of this, solve for one variable in terms of the other one, plug it in, and then go back and do it over again. So what I'm trying to say is I could make life easier for myself if I rotate my coordinate system. If I make my x and y axis instead of just normal horizontal and vertical, if I say, well, let's let x lie in the direction of tension and y lie in the direction of the normal force, life will be a bit easier. And that's usually a good way to approach any type of problem where you have an incline. Is generally speaking, when you're dealing with an incline, it's almost always easier to rotate your axis and solve for the forces or whatever, the accelerations in that rotated coordinate system. It'll always save you at least one step, maybe more. So let's do that just to confirm to ourselves that we're actually going to get the same solution. All right, so I have this sort of a problem. I have a sled on a hill. This is 30 degrees. But now instead of solving this problem like normal, here's the normal force and then gravity is straight down, I'm going to rotate. And I'm going to say that this is my x direction and this is my y direction. So tension now lies in the x direction, normal force lies in the y direction. So I don't have to break those two things up, those two forces up into their components. The only force that I have to break up into its components is the gravitational force. So instead of having to break up two forces, I only have to break up one. All right? Now the only reason that this is a bit more tricky is because now I've got to figure out the triangle. All right? I've got to draw a triangle so that I can actually break this thing up into its x and y components. All right? I'm going to just arbitrarily choose this triangle. So the triangle goes from, let me do that in a different color to make it clear. Triangle goes from the tip of the force due to gravity and then perpendicular to the x-axis over the y-axis. So here's the triangle that I need. So I want to solve for fg sub x and fg sub y. Okay, those are my new x and y components. So the only trick here is determining what is 30 degrees. So some angle in here has got to be 30 degrees. Either this angle or this angle is 30 degrees. Which one do you think it is? You think it's the lower one? How would you figure this out? Rather than guessing and relying on the picture to be to scale.
It'd probably be a lot easier to visualize if we made the triangle a little bigger.
Bigger triangle.
One of them is 30 degrees, so that it goes all the way to the bottom of gravity. So you have two right triangles next to each other.
You want me to extend the slope?
Yeah.
I could do that, maybe. That's going to help. If that'll help you, I will do it. Maybe it'll help me. All right, so did I get you? Green will extend down to like here is what you're saying?
Yeah, and then it goes to the bottom of gravity.
Okay, if that helps.
And then it's just geometry problem.
It is just a geometry problem.
An easier one.
Because you rotated it, you rotate it back to the normal force, the triangle.
If it's a right triangle, then the angle that makes the
Yeah,
y-axis
gotcha,
is
it's just
6
rotated.
degrees.
Okay, so what I'm trying to get at here is you guys probably might, I assume you all have different ways to think about this. And I'm going to tell you my way. All right, my way involves rotations, just like I said before. In order to get to this slope, this is my new x-axis. This slope is my new x-axis. The bottom of the slope, this horizontal line, that was my old x-axis. So in order to get from old to new, I rotated 30 degrees in the counterclockwise direction. So that means that if I start from my old y-axis and I rotate 30 degrees counterclockwise, I'm going to get to my new y-axis. Not new. All right? Even though this is the negative y-axis, it doesn't matter. So I start from my old negative y-axis and I rotate 30 degrees, I get to my new negative y-axis. So what I'm looking for is this, old negative to new negative, and that's what I have right here. Here's my old negative y-axis. I rotate 30 degrees, and I get to my new negative y-axis. Again, that's how I think about this. If you want to be more geometrically correct and sort of follow, interior angles and stuff like that, do it. but I always look for rotations. I find one of my original axes, I rotate 30 degrees to get to my new axis. That's all. Does that make sense, at least? This is generally the hardest part of these problems, is identifying this angle. Okay. So now I know what my angle is, so I can break up gravity into its x and y components. So the force due to gravity in the x direction, which is the component that lies along this line right here, that's got to be the sine of 30. So Fg times the sine of 30, because this side is opposite of my angle. The y component, Fg sub y is Fg times the cosine of 30. Those are the only two things I need to break up into their x and y components. Now let me point out something else really quick. If there was no tension here, if this thing was accelerating, it would be accelerating down the slope. It would be accelerating in the x direction, the negative x direction. Okay? I don't have to break up the acceleration into its components. So that's another reason why this rotating the coordinate system is easier, because now if you throw in an acceleration, it at least just lies in the x direction. You don't have to break up the acceleration into x and y components. All right, in this problem, the gravity is pointing straight down. The force due to gravity in the y direction is pointing in the negative y direction, and the force due to gravity in the x direction is also negative, so I've got to make sure I include my negative signs. After I've done that, I can do the summation of my forces. So some of the forces in the x direction, I'm just going to write those down. I know that I have tension pointing up and to the right. All right, it's not t sub x. T sub x is equal to t because we have a new x direction. And then going down the slope, I have my x component of gravity, Fg times sine of 30. Since there's no acceleration, the term on the right is equal to 0. So like I said, this is a bit easier because now I could just say, well, tension, I could just solve that. I don't have to solve for something else in terms of tension. Tension is equal to Fg sine 30. All right? And if you do Fg sine 30, then you should get 38.5 newtons. So we solved for tension right away. We didn't have to do any sort of tricky back substitution stuff. So that means that if I solve the Newton's second law in the y direction, I'm going to get an equation for the normal force. So my equation is n minus Fg times cosine of 30. That's equal to mass times acceleration in the y direction, which again is 0. So once again, I didn't have to do anything tricky. I just know that the normal force has got to be equal to the F sub g times cosine of 30. If you solve for that, you're going to get 66.7 newtons. All right, so I would argue that doing it with the rotated coordinate system is easier than not. All right, certainly these equations are simpler. Not that you couldn't do it the other way. We did it the other way, but I think this is just a little bit easier and less prone to error. The only tricky part about this bit is making sure you get the angle right. So give yourself some practice. You'll do that on the next homework. Make sure you understand how to get this angle, however you want to figure out how to do it.